Hypochlorous acid has the formula HOCl. Each chlorine contributes 7 valence electrons, the oxygen contributes 6, and the hydrogen contributes 1, for a total of 14 valence electrons. We can allocate 2 of the electrons here, and it satisfies the duet rule. 6 more around the oxygen satisfies the octet rule, and then the last 6 here, including the bond to oxygen, satisfies the octet rule for chlorine. So we see that while we can expand the octet for chlorine under some circumstances, for this particular compound, there is no need to do so. Chlorous acid has the chemical formula HClO₂. To form its Lewis structure, we notice that there are 2 oxygens, each contributes 6 valence electrons, so that gives us a total of 12. There's 7 from chlorine and 1 from hydrogen, which gives us a total of 20 electrons. Chlorine is our central atom, and the oxygens are attached to it. The acidic hydrogen is attached to one of the oxygens. So we can allocate the electrons satisfying the duet rule for hydrogen, the octet rule for oxygen, and oxygen over there, and for chlorine, and we have no need to expand the octet for the chlorine, at least for this particular resonance structure. It turns out we can actually draw a second resonance structure for this compound. Here we have a second resonance structure for chlorous acid. Notice that in this case we have a oxygen double bound to chlorine here. It still is using the same number of electrons. We still have 20 electrons, but we notice for chlorine that we have 2, 4, 6, 8, 10 electrons. So we're allowed to do that for chlorine because chlorine is a third row or later element, so therefore we can expand the octet for chlorine. We don't have to necessarily, but we can, and in this resonance structure we're able to do so. Chloric acid has the chemical formula HClO₃. We generally considered chloric acid to be a strong acid. To construct its Lewis structure, we notice that we have 3 oxygen atoms. Each contributes 6 valence electrons for a total of 18. Then we have 7 more from the chlorine atom and 1 electron from the hydrogen atom, which gives us a total of 26 electrons. One way in which we can allocate those electrons is by connecting all the atoms by single bonds. So that satisfies the duet rule for hydrogen. We satisfy the octet rule for each of the oxygens and for the chlorine. So we notice we have 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26 electrons. So we've used the proper number of electrons, and we're able to satisfy both the duet rule and the octet rule for this particular resonance structure. We can also draw 2 more resonance structures, which we'll demonstrate now. For this resonance structure, the oxygen is connected by a double bond to the chlorine, whereas the other 2 oxygens are connected by single bonds. We notice that we still use the same number of electrons, 26, but now we have 2, 4, 6, 8, 10 electrons around the central chlorine atom. This is allowed because chlorine is in the 3rd row, so it can expand the octet, because once we get to n = 3, we have 3s, 3p, and then 3d orbitals which are available. Also, chlorine is a larger atom, and generally we can put more electrons on the larger central atoms. For the final resonance structure, we have 2 oxygen-chlorine double bonds and 1 single bond. In this case, we see that we have 2, 4, 6, 8, 10, 12 electrons around the central chlorine atom in this particular resonance structure. Perchloric acid has the chemical symbol, the formula HClO₄. Each of the oxygens contributes 4 valence electrons, so that gives us 24 electrons. The central chlorine atom gives 7 electrons, and the hydrogen atom gives 1 electron. So therefore we have another 32 electron system, and we can draw numerous resonance structures for this particular acid, which is one of our most important strong acids. For the first structure, we're showing one where we have a single bond to this oxygen atom, but we have 3 double bonds otherwise. So notice that we have 4, 8, 12, 14 electrons around the central chlorine atom in this particular structure, whereas we have a normal octet around each oxygen and the normal duet around the acidic hydrogen atom. For the second resonance structure of perchloric acid, we have 2 chlorine-oxygen single bonds and 2 chlorine-oxygen double bonds. In this particular case, we have 4, 8, 10, 12 electrons around the central chlorine atom. For the next resonance structure, we have 3 chlorine-oxygen single bonds and 1 chlorine-oxygen double bond. In this particular case, we see that we have 2, 4, 6, 10 electrons around the central chlorine atom. The final resonance structure consists of 4 chlorine-oxygen single bonds. In this particular case, chlorine has an octet, but it has not been expanded, so it has exactly 8 required electrons. Important thing to keep in mind is that for perchloric acid, not a single one of the resonance structures is the correct structure. The correct structure is an average of all the possible resonance structures. They don't necessarily all contribute equally. Some contribute more than others, but they all are mixed in for the average final true structure. Here we have one resonance structure of perbromic acid. Notice that all we've done is to replace the central chlorine atom with a bromine atom. Since bromine and chlorine are in the same family, they contribute the same number of valence electrons, the structures are identical. But keep in mind that just as for perchloric acid, perbromic acid will have the same number of resonance structures. Once you know how to do the series of hypochlorous acid, chlorous acid, chloric acid, and perchloric acid, by analogy, merely by replacing the central chlorine atom with a bromine, you can do hypobromous acid, bromous acid, bromic acid, and perbromic acid. The final important member of the halogen family, after chlorine and bromine, is iodine. So you might imagine that we could simply replace the chlorine or bromine at the center of perchloric or perbromic acid with an iodine to get the analogous compound, periodic acid. And we do. So here we see one of the resonance structures of periodic acid. Recall that this will have the same number and type of resonance structures as did perchloric and perbromic acid. And you can go back and examine the series of hypochlorous, chlorous, chloric, and perchloric, and you should be able to construct hypiodous, iodic, and periodic acids by analogy.